Welcome to Donkey Learning IT, where we are going over IT related equipment, both hardware and software, in what I call Donkey style. So this is part 2 of a video series where I'm concentrating on the Cisco 2960 series switches, mainly on the hardware. In part 1 of this series I have looked at the disassembly and on the power supply itself. In this part 2 of the video I will concentrate instead on the motherboard, and at the beginning we're gonna look from the perspective of a CCNA or a CCNP. Where are the components like ASIC, route processor, flash, RAM and so forth, which is part of a Cisco curriculum. Then, after I'm done with that, I will remove the board from the case. Then I will also remove these heat sinks, and I'm gonna really get the board pretty much naked, so to say. And as we know, once you remove the heatsink, things gonna get hot in here. And in addition to that, of course, I'm gonna look on the individual components with 10 times magnification, and we're gonna go over from the perspective of a repair technician of which individual component does what in this particular circuit. From the perspective of a CCNA or a CCNP, what you are interested in is that this is here the route processor. This is, of course, a specialized processor. I will go later in detail what this actually is. At the end of the day, let us just stick to the notion that this is the route processor. It's called the Yeti 2. Well, most probably it's coming from Area 51, who knows what. Then these two chips here are the flash chips. This is where the iOS resides, in binary format, of course, as a 32-bit ELF binary. And this will be then decompressed through the route processor into the RAM. This is a 64 megabyte RAM chip here. And considering that the 2960G series switch, at least this particular one what we are looking at, does not have NVRAM chip itself, so a non-volatile RAM, what they are doing is that they are actually partitioning the flash chips. And if you look as an example, you do dir flash double dot from the command line on a working device, what you will see is that on the flash chips you also have the startup config.txt file. So due to the lack of an NVRAM chip, they are partitioning this flash, and this is where also your configuration is stored as well. On all the routers, there is a separate chip to hold that configuration. Next we have here, of course, the heat sinks on the two ASICs. We're gonna look at these ASICs later. Main thing is that, anyway, these are definitely Cisco very specific application specialized integrated circuits. Next to the two ASICs, we have one of the PHYs, which does nothing else but puts really now the frames or packets, depending whether you look at which you prefer. PHY chip really puts the information on the wire itself. And if I move the switch a little bit, now one can see that this PHY chip is shared between the SFP, so the small form factor pluggable port, and between this standard RJ45 gigabit port. This is why you cannot have two cables plugged into this port. So this is not a 9-port switch, it's only 8-port switch. You can use either this or this. In addition to this PHY chip here, we have 7 more PHY chips here below this plastic, which is nothing else but just redirecting the LED light to the front of the case. I hope you can see it. And these 7 PHYs are then dedicated, of course, for every of these 7 standard RJ45 gigabit ports. Then this particular chip here, let me get it out of the shadow. So this particular chip here is your serial console chip, which practically is just communicating between the main route processor and your serial console cable. And I think for the CCNA or CCNP candidates, this is pretty much what you have to know about where do these components reside. And now I'm gonna remove the board, and we're gonna look from the perspective of a repair technician. So we're gonna go into very deep detail. If you are studying for a CCNA or CCNP, of course you should still follow around so that at least you get a grasp of how complex these devices actually are. But keep in mind that this is not really necessary for your certifications. No one gonna test you how does the device really looks inside. This is just a passion of mine, which I really like to look into deep detail of what really goes on inside something, not just, okay, there is something, I plug it in, it works. In order to remove the motherboard, you need to remove all these screws. You're gonna need a Torx T10 screwdriver in order to do that. Please take special care that there might be little voltages present in the power supply. So do not attempt any of these things what I'm doing here, except if you're a repair technician or you really know what you are doing. After you removed all these Torx T10 screws, you're gonna have to lift the back of the board a little bit with a flathead screwdriver or with a flat tool. And then what I normally do is that after I lift the board, I just push the whole board backwards a little bit, and then I can lift it out, because these plastic, after you have removed now these plastics, we can look at the main features of the board. This is where the power supply comes in, the plus 12 volt DC. This is again belonging to the power supply and the inner power distribution in the board for different chips. This part here is a glue logic. Then this part here is the main clock generator. Of course, this is then the flash, as I already mentioned in the beginning of this video. This is the main CPU. These are some ASICs. This is the main random access memory. And of course, then these are the PHYs, which are just the physical input-output chips. Okay, so we're gonna look at the power supply portion of the board first of all. Since we cannot see much from this distance, I need to put in a different lens and make a 10 times magnification. Okay, so here is the 4-pin power connector where the power comes in. Next to the power connector we have some minimal filtering again. And since none of the devices work at plus 12 volt DC, the 12 volt is directly fed into an international rectifier buck converter, which also contains the field effect transistors inside. By the way, if someone could explain me or write me a message, how can one actually interpret the datasheet of these devices, or where can I find the datasheet for this particular international rectifier part, I would be really happy and grateful. Nevertheless, I digress. So this buck converter here makes out of the plus 12 volt. It generates, as you see here, the test point. It makes 3.3 volt DC, which is of this inductor here belongs to the international rectifier buck converter, and through chopping the 12 volt DC through this inductor, we are getting this 3.3 volt DC. Then this 3.3 volt DC is then chips. I will tell you the serial numbers, or not the serial numbers, but the part numbers later. I will also link them in the description of the video. As usual, I will use the German alphabet when I'm calling the name of the components. So, nevertheless, there are several of these Maxim buck converters which are fed from 3.3 volt. These can go up, these Maxim converters, up to a 3.6 volt input voltage. And if I remember correctly from the datasheet, they can generate maximum of 0.6 times the input voltage. So in this board, they are used to generate voltages like this 1.2 volt or this 1. So these two parts here, the bigger ones, that one and this one. Let me zoom in a little bit more so we can see the part number. The camera will shake because at this magnification a tiny little movement makes a huge difference. Sorry for the motion sickness. Okay, so it is Maxim 8566E, which is a buck converter which has the power field effect transistors built into the device already. Then we have another Maxim 8566E and a teeny tiny, right after these Maxim parts, which are generating then this 1.2, 1.8 and 2.5 volt. Then we're gonna find an Interseal 8700IBZ, which is a very nice quad power sequencer. The ISL 8700 series of chips, in my view, are pretty nifty little chips, and they are a so-called quad power sequencer. And what they do is the following. There are 4 outputs which are pretty much like digital outputs, and in the case of the ISL 8700, these outputs normally are pulled to low. Then, once the power is coming in, as you see on the left side, there is a resistor divider, and there are this resistor divider is connected to 2 pins which are serving as input pins. This is the so-called under voltage, and this is the over voltage protection pin or detection pin. What happens is that once there is a given amount of potential difference or power, so to say, to the chip, then the chip will enable, as long as neither the under voltage or the over voltage pins are triggered, because there is a comparator inside. So as long as none of these are triggered, it will allow the first output to go high. Once that happens, it will discharge this timing capacitor here, and it will start to charge it again. Namely, inside this chip there is a constant current generator, and through this constant current generator it will charge the capacitor. Of course, these resistors then will play a role on the timing, and based on the resistor values what you select here, then you can really set up how does the power sequence come in to play. Namely, once the capacitor is charged up, then it will be discharged again, then you enable the second output, then again through this second resistor charge the timing capacitor, and you do this again over and over for the fourth output. And this is how the power sequencing is done. Next to the ISL, this interseal quad power sequencer chip, we're gonna find already the glue logic. So these are Texas Instruments. I've written it down. They are SN74LVC 245A, which are practically octa bus transceivers. So this means that somehow practically if you send in a signal, you can select whether you are communicating to one device or another via these bus transceivers. Next to these 8-bit octa bus transceivers, we're gonna find also from Texas Instruments, the SN55HC595, which are 8-bit shift registers. There are 3 of them on the board, and these shift registers are directly communicating with the Marvel gigabit PHY chips. I would not think that they can pump enough data through for a gigabit speed. I would expect they are more like doing some serial to parallel data conversion when they are just addressing the particular PHY chips in question to which one the ASIC wanna communicate. Next to these 8-bit shift registers, we are coming towards the clock circuit for the main route processor here. So it's a 25 megahertz crystal. I think that the route processor runs at around 400 megahertz, so they are using who knows what harmonics via a phase locked loop from this quartz crystal. And next to it we have another Maxim. What is this? Let me zoom in. Oh yeah, it's a Maxim 8643E again, together with the necessary inductor to generate 1.5 volt, which is then of course used for the Cisco Yeti 2 route processor. The chip which makes the clock frequency is a Pericom P149 FCT 20807 HA. I mean, Pericom is pretty much knee deep, so to say, in the network related chips, especially when it comes to clock devices. So this is, as far as what I found in the database, this seems to be a low jitter, low skew clock buffer when there is one input and it has 10 outputs for 10 different devices. Considering that this is an 8-port switch, it makes sense that besides the 8 ports you need at least 8 clock outputs, which are then synchronous. And of course you need to also have, have a clock output for the CPU and for the ASICs. Next to this Pericom clock buffer, we're gonna find, this is from most probably from Texas Instruments as well, I'm not quite sure. It's an SN74 LVC 126A, which is a quadruple bus buffer. So what this thing does here is that it generates or it communicates between the flash and between the CPU when the CPU needs to access the flash. then these two chips are used for that. The two flash chips, both of them are TE28F128, which are nothing else but from Intel. These are 228 megabits, which is 16 megabytes per piece. And what happens is that one of the bits is written in one of them and the other one in the other one. So practically the data is so-called interlaced. There is an odd and an even data flash. And this is how you reach from the 216 megabyte flash chips. You're gonna get a combined 32 megabytes, which is then addressed by the main route processor here. Talking about the route processor itself, as you see, this is a Yeti 2. Well, I think the English name for Yetis is Bigfoot. I think Yetis are rather rare, and no wonder that this is not really a Yeti. Namely, this chip is nothing else at the end of the day but IBM PowerPC 405 core, and which is used in a lot of embedded systems and routers, or in this case switches. It's a 32-bit RISC processor, and of course Cisco have taken this PowerPC 405 core, and it have included some additional FPGA or field programmable gate array parts, and also some of these components which are like equivalent to a PC South bridge and North bridge, that the route processor can communicate with the ASICs, and it can communicate with the flash, and of course it can communicate with the RAM as well. Note that they have actually already they drilled holes for potentially mounting a heatsink on the route processor itself. Nevertheless, this thing runs so cool that I'm not wondering that they didn't spring at the end of the day to put a heatsink on this route processor here. Then, next to the route processor, we have a 64 megabyte RAM chip from Micron Semiconductor, which is making most of the RAM which is included in Cisco devices. It's a 46V32M16. And next to this RAM, we're gonna find one of these somewhat specialized chips, which is nothing else but a linear regulator, but it was already made in particular for DDR memory. So in addition to the voltage which is provided to feed the chip, it also provides 1/2 of this particular voltage, since in the case of DDR we are taking 2 bits both when the clock goes up and when the clock falls down. This is why you need to keep the memory bus at 0.5 times the voltage what you feed for the memory chip itself. And this is what is happening in this linear regulator chip here. Between the main route processor and the main large ASIC, which is generating a little bit more heat, this is why it is having this black oxalated aluminum heatsink. So between the two chips, we're gonna find on analog devices ADT75, which, let me zoom in a little bit. This is a teeny tiny component. So this is nothing else but a 12-bit temperature sensor, which is having a resolution of 0.06 degrees Celsius roughly. So it's no wonder that it is right next to the components which generate heat. And Practically it's measuring the temperature around the ASIC and around the route processor itself, and it communicates most probably with the route processor via the inter-integrated circuit or IC2 bus. These very small 5-pin SOP23 packages with the marking of 7Z25L, if I can trust the database, these should be from Fairchild, and they should be ultra high speed buffers with the longer original part number of NC7SZ125M5X. Right next to the analog device's temperature sensor, we're gonna find, at least I found a mystery component. It is from Integrated Circuit Systems manufacturer. The chip number is UD8808265, and I could simply not find anything useful on what the heck is this component. The only result which I got was that this could be clone of the old school Z80 Zilog microprocessor made in East Germany, and quite frankly I do not believe that that's the case here. I mean, what would a Z80 CPU do in this board, honestly? So if you know what this part is, please leave a comment in the description below. I'd love to figure out what this is. If I would need to take a wild guess, I would say that this is where the boot ROM is residing. So then this is used to boot the CPU first, and so this would be practically, in Cisco terms, the ROM mon. However, since I have no idea what the part really is, this is just a wild guess from my side. Then next to it, we're gonna have again a Pericom clock buffer with 10 port outputs, and for whatever reasons we also gonna get a Cypress. It's a Cypress Comlink series CY2 CC8100-XT1, which, I mean, I really don't get it. So this Pericom is a clock buffer for 1 port in, 10 port out. This is also a clock buffer with 10 ports out, and of course we have the quartz crystal next to them. But why did they use two different devices when at the end of the day they do the same thing? This is again a strange mystery to me. If you know, just let me know what you think. The PHY chips, which are then directly connected to the RJ45 jacks, are from Marvell. They are the 88A112-NNC. The PHY chips themselves are just directly connected to the RJ45 output, and inside the RJ45 connector here there is the built-in magnetics. Then this is the output for the console cable coming in, which is normally this teal or blue greenish colored flat Cisco cable, so-called rollover cable. This chip is nothing else but a Texas Instruments version of the RS3232 driver, which is practically taking in the plus 3.3 volt signals. It can make plus minus 12 volt output, which is necessary for the serial communication. Then this chip here is a Texas Instruments SN54HC595 8-bit shift register And what it is doing is that, as you see, there is one serial signal coming into the chip. And practically this way they can use only 2 traces on the PCB, which of course makes the PCB design a lot easier. And then they are practically shifting the bits inside. So this way they can address all the 4 LEDs which are displaying the flash and the different modes of operation of the switch. A similar thing happens with the LEDs which are right next to the RJ45 ports. Here you can see the trace that they are directly going to these 8-bit shift registers, so they do the same. They have the same functionality here, that the CPU sends some information to these chips through the serial interface, and then they fan out to multiple LEDs on the board. As I promised, next I will remove the heat sinks from the 2 ASICs, and we're gonna look what they are. I would expect that they are some Cisco very specialized parts. Most probably we're not gonna find out anything about them, but nevertheless, I'm just interested how do they look. Okay, so I managed to remove the smaller heatsink, and this is Renesas technology part for short. It's an R8A20300ABG. I tried to look around on the internet. I could not get any access to the datasheet of this particular chip. However, by searching around, I found some similar circuits in the database, and the circuits which are related are practically nothing else but ternary content addressable memory. So this is where your TCAM table resides, or the CAM table for Cisco CCNAs and CCNPs. And it practically it stores the MAC addresses in this very fast static random access memory, and on top of that it also does deterministic searches to so it has a search engine inside this chip, and the search engine is then looking up what has to happen with the packets. And even though I promised to remove the heatsinks from both ASICs, well, I didn't manage from the second one, even though, as you see, I have removed these plastic studs. Actually, the heatsink is epoxy glued to the chip, and I simply cannot remove it. I tried it with the good old dirty trick of trying to freeze it. I could still not get it off, even though I wasted like a quarter of a can of freeze spray on it. If we flip the board over to check it out from behind, well, there is not much to see here. There are mainly just passive components, mainly decoupling capacitors around the large ASICs and around the CPU. These two features, what you can see here, these are nothing else but some of these silica pads which are providing heat coupling between the bottom of the board and the case, which acts as a heat sink, and on the other side of the board. So this sums up the fun for today, what we had with this Cisco 2960G switch. I really hope you have learned something from this two-part video series.